This is MAM seminar, Mathematics and Applied Mathematics seminar at the Mathematics and Applied Mathematics environment, research environment at Division of Mathematics and Physics at Moldavian University. And our speaker today is Abdennour Kitouni, who is a researcher with us, and he will start his series of lectures on n-ary algebras and Hom-algebras. Today's lecture will be introductory overview of lecture about n-ary algebraic structures, introduction to n-ary algebras, and overview of n-ary algebras. And then there will be several more lectures which will be announced further on in this course and in this series of lectures. For PhD students, it is a course, but for all others, it's an interesting series of lectures, which I hope many of you can attend and benefit about from. And we will now start. And Abdennour, it's your you start your lecture. Yes.
Thank you, Sergei. Hello and welcome, everyone. So today we will be talking about n-ary algebraic structures. I will present a short overview of how this research field began, so to say, and various types of, or should I say, the most known types of n-ary algebras and some of their properties. So we will not go very deep inside today, but it will be rather broad than deep. So to begin with, let me recall a few basic algebras definitions that we will build on, so to say. An algebra is a vector space together with a bilinear multiplication. It is said to be associative if its multiplication is associative. We know also that keep in mind that in some conventions by some authors, algebras are required to be associative, and they use the term non-associative algebra if it is to mention that an algebra is explicitly required not to be associative. A type of non-associative algebra would be Lie algebras, which are vector space with a bilinear multiplication or bracket that is skew symmetric and satisfies the Jacobi identity there. This Jacobi identity can be written using skew symmetry under a different form, also known as the Leibniz rule. Look at this first form is saying that the cyclic sum of the nested brackets over three elements is 0. However, this is saying that the left multiplication, for instance, has a derivation-like or differential-like property, the left multiplication by x. A very common construction of Lie algebra is to take an associative algebra and to take as a bracket the commutator, which is xy minus yx. And I note this one because we will have some generalization of this one later. So now to move on to n-ary algebras. An n-ary algebra is just like this. However, the multiplication is n-linear, which means that it requires n entries or n factors at once, not 2. So the work about n-ary algebra began quite early. So this was as far as I could trace back, but this is probably one of the very first works on n-ary algebras or ternary algebras, for instance, Lie and Jordan triple systems, which are in their first realizations just iterated multiplications which happen to have applications or uses in geometry in submanifolds of Lie groups and in symmetric spaces. Also, this article by Kurosh is what's cited as the earliest reference for n-ary algebras in general, as a general theory. We have those three authors mainly, and so I cited three articles, but several other articles by same authors and around them, generalizing rings, so to say, associative algebra. So we have ternary algebra, associative triple systems, which is also another way of saying that. A few articles of back at this time on associative generalization of associativity are in German, as this one. And then the first work, first part of the work was done on ternary algebras, that is n is equal to 3, and then afterwards generalizations to n came. On the other hand, we have n-ary generalization of Lie algebras. A lot, so others refer to Nambu's generalization of Hamiltonian dynamics as the very first appearance of such a bracket, even though Nambu didn't really explicitly show or say that this was a generalization of Lie algebras. And the work following from Nambu's work was done later by Takhtajan. On a completely different axis or different group working with exactly the same objects, we have Filipov, which introduced actually first n-Lie, so-called n-Lie algebras, which are a generalization of Lie algebras, and then several others following, but I cite those, so to say, which mark the beginning of n-Lie algebras. And now can look at those four articles, which are examples of more recent applications of n-Lie algebras in physics, which made a lot of researchers look back again and work much more on n-Lie algebras. So let's begin with some preliminary definitions. An n-ary algebra in the most general shape is a vector space equipped with an n-ary multiplication that is an n-linear map on A. I put in here this definition if Lars is here with us. Some authors like to use the universal algebras convention, so I'd rather introduce this definition so that if you read it, you know what it is about. So an n-ary algebra is a linear omega algebra where omega contains only one n-ary symbol. So this is for short, to say shortly, an algebra which is in this sense a an algebraic structure in the most general case. Linear is to say that it's based on a vector space. So we have vector space and more. And contains only one n-ary symbol means that we have only one operation, which is n-ary. So for example, if we take a normal associative algebra and then we take the n-fold iterated product, then we get an n-ary algebra. Or the same if we take nested brackets of a Lie algebra. A morphism of n-ary algebras looks like this. So we take two n-ary algebras and we have a linear map between them that is compatible with the operations. That is f applied to m of x1 to xn is mu, which is multiplication in the image of the images of x1 to xn. And when we have an n-ary operation or an n-ary algebra, we also consider the following generalization of a derivation. So you can look at this f as satisfying a generalized Leibniz rule for the n-ary multiplication. So I take the sum over all of them, and in each term of the sum, f is applied on only one entry of the multiplication. So a few more properties. An n-ary algebra is said to be symmetric if it's invariant under any change of order of elements, that is any permutation in Sn. Or it is skew symmetric if when I change the order of the elements, I get some sign, which is the signature of the permutation I used. A subalgebra of an n-ary algebra is a linear subspace that is closed under the n-ary multiplication. So if I take n element and then multiply in S, their product, n-ary product should be in S. And an ideal is a linear subspace for which all products, including n-1 elements from the whole algebra and one element from the subspace, should be again in the subspace, no matter the order of or the position of S, be it beginning, middle, or in the end. So if the algebra is symmetric or skew symmetric, then it is sufficient to take only one of these. For example, we take only this one in the end. This one is sufficient in that case. So now I will present a little bit of the general idea on how all these various types appear, various types of n-ary algebra that will come now. So if we take binary algebras or normal algebras, so to say, we have also different types of n-ary algebras. However, so the properties defining different types of n-ary algebras are generalization of what we saw just now: associativity, Jacobi identity, Leibniz rule, and so on. However, those in binary algebras can be generalized in different ways. They come from 2 or 3 interpretations of the same identity, which are equivalent and which would be not equivalent anymore in the n-ary case. So for associativity, we can look at associativity as the nested or iterated multiplications are equal no matter how we use parentheses. Or we can look at it as the associator, which is xyz minus xyz is 0. So those are equivalent in the binary case, and they are not equivalent anymore in the general n-ary case. An n-ary associative algebra is an n-ary algebra is said to be totally associative if it satisfies this condition. So we have 2n minus 1, which is the equivalent of 3 elements. So the necessary amount to fill in 2 nested multiplications. And then we put them together, and doesn't matter where the second multiplication starts or ends, the result should be the same. So we can look at it here. So we take the inner multiplication on the n first element, or from second to n plus 1, or third to n plus 1, or and so on. All results are the same. So, for example, we have this example taken earlier. The n iterated product of an associative algebra gives an n-ary totally associative multiplication, or an n-ary totally associative algebra. Conversely, every totally associative algebra can be viewed as a sub-algebra of such an associative algebra. We have also a few variations coming from this same direction. A weak totally associative algebra is an algebra where we have this total associativity holds only for the beginning, and the second multiplication is in the beginning or in the end. Or we have this second variation for n equal to 3. An algebra is said to be totally associative of type 2 if it satisfies this condition. So it's the same as the total associativity we saw just now, but in the second member of the equality, we have these the order of elements inside this second multiplication, which are reversed. So here I have x, y, z, u, v. Here I take x, and then y, z, u in a different order, and then v. However, for the third one, I go back to the initial order of elements x, y, z, u, v. So these are algebra appeared in some kind of in some application related to this very example. So I take the vector space of real matrices, can be complex also. And we take this ternary multiplication, A times transpose B times C. So this one would satisfy the second type, total associativity. And these algebras appear in the study of generalized inverses of rectangular matrices, which we had a seminar related to these a few weeks ago. This same construction can be generalized to any set of group morphisms. So we take two groups and the set of morphisms between them, and then we need some transformation which acts the same in a similar way as the transposition of matrices, and we can construct a similar structure. Those are called Hessian rings. Another definition, so if a totally associative algebra is said to have a unit if we have an element E such that the product of n-1 copies of E with any element in any possible order gives the same X. Note that this E in the n-ary case is not unique as in the usual binary case. Now we move to the other variant, which is taken as the associator is 0. So an n-ary algebra is said to be partially associative if we have this condition satisfied, that is, the sum of all of these nested multiplications of 2n-1 elements is equal to 0. We have several variations of these requiring different signs in some places of this sum. These partially associative algebras seem to be much less common in the literature than the totally associative algebras. So now for those generalizing Lie algebras, we have also the same thing happening, two different interpretation of Jacobi identity give rise to two conditions which are not equivalent anymore. So we can see, look at this side of it. The left multiplication operator is a derivation, or what we call the Leibniz rule, or the sum over the whole symmetric group of all possible orderings of the elements inside the bracket gives 0. And there are also other minor, so to say, less common definitions, but those two are the most common. So the first one is called n-ary algebra. An n-ary algebra is a skew-symmetric n-ary algebra that satisfies this identity. I take, so here I have x1 to x minus 1 defining this left multiplication operator applied on the bracket y1 to yn, and here I have this sum each one we have the left multiplication only in one position. So this is saying that this left multiplication operator is a derivation. Since we have skew symmetry, it's also possible to consider the right multiplication operator and gives exactly the same results. So this identity is called fundamental identity or Filippov identity. And n-ary algebras can be found under those names. Some people call them Nambuly algebra, referring to this physicist, or Filippov algebra. The name itself, this very name, n-ary algebra, comes from the work by Filippov, who defined them first. So I stick with it. The other variant of n-ary Lie algebras is this one called n-ary generalized Lie algebras, which are skew symmetric and have this condition: take two nested brackets and the sum over s to n minus 1 is 0. It is possible also to simplify this by taking a subset of the permutation, which are called the shuffles, n minus 1 n shuffles, which keeps these part ordered and this part ordered, so to say. So since we have skew symmetry, this is possible to do. And other names also, because there's not only one terminology which is fixed. Those are also called Lie n algebra in this order, Lie and then n, or homotopy n-ary algebras. Now I would like to present a few examples of these algebras. So first, take the smooth functions over Rn and take this bracket. So I take n functions and compute this determinant, the Jacobian. So this Jacobian is with this space is an n-ary algebra. So the first one, which is for which right multiplication or left multiplication is a derivation. Now we take a finite dimensional example. I take n plus 1 dimensional real vector space again with take this basis, and I define an n-ary n-linear skew symmetric map by the following formula. So since we have this bracket is supposed to be n-linear and skew symmetric, then it is sufficient to define it on basis elements and only in a given order. So if I take, for example, E1 over here, we can get back to one of these by skew symmetry. And this one is also an n-ary algebra. Look carefully at this one. What happens if I take n to be equal to 2, then the dimension would be 3-dimensional real vector space, and those formulas would be exactly those defining the cross product on the real space. So this one is also a generalization of the real cross product. Now to another example, take again the smooth functions and on the real line this time, and take this determinant of first all of these functions, then first derivative, second derivative, and so on until derivative n minus 1, or so-called Wronskian. So this Wronskian defines an n-ary generalized Lie algebra, which is the second kind of n-ary Lie algebras we defined. So some other types of n-ary generalization of Lie algebras, we have a Lie triple system is a vector space with a trilinear map. So this definition holds only for n is equal to 3. This bracket is skew symmetric in its two first entries, and the cyclic sum of the bracket is 0, and it satisfies the fundamental or Filipov identity. So this one is the same as this one. So if you recall the example we defined earlier, nested brackets of a Lie algebra, these define a Lie triple system, and this was the very first example that came to existence, which was used to study submanifolds of some Lie groups. And another type of related algebras, so to say, is n-Leibniz algebras, which are a kind of non-skew symmetric version of n-Lie algebras. So they satisfy the Filipov identity without being skew symmetric. So to be accurate, these ones are called left n-Leibniz algebras, and we can define also right by reversing all of these, taking this multiplication to the right. Lie triple systems that we just saw are a special case of these. So now I would like to present a few properties and relations between those various types, like what we saw earlier with the commutator of an associative algebra and so on. So first of all, between those different generalization of Lie algebras, we have an n-Lie algebra is always a generalized Lie algebra. However, the converse is in general not true. So if it satisfies the fundamental identity, which is the generalization of Leibniz rule, then it satisfies this, that the sum over s to n minus 1 is 0. But the converse is in general not true. As an example, the Wronskian we saw right now is an n-ary generalized Lie algebra, but in general it's not an n-Lie algebra. Even if we take some generalization of these, there's very interesting work on that, considering those Wronskian in a general abstract case, and then which of them are n-Lie algebras and which of them are not. So now to one generalization of the commutator. So if you take an n-ary partially associative algebra and we take sorry, I have a slight misprint here. So here I should have the signature of sigma. right? So the sum over the whole group of permutation, and for each permutation I use the sign of it. As for binary, I have xy minus yx. So this one gives an n-ary generalized Lie algebra. The other properties related now to, or construction of, related to n-Lie algebra. So if I take an n-Lie algebra and then take the fix one element or the partial bracket, then I get an n minus 1 Lie algebra. That is, this bracket is exactly of the same type if I have one element fixed. Now, if I take an n-Lie algebra and then a linear form on L that for which the bracket vanishes, then we have this cyclic sum gives rise to a ternary bracket, which gives a 3 Lie algebra. If we do this, the same thing with an n plus 1, with an n Lie algebra, then we get an n plus 1 Lie algebra. And again, if I take a totally associative algebra, ternary one, and then we define the following trilinear bracket. So this one is, again, another generalization of the commutator. This one for totally associative algebra, a different generalization gives a Lie triple system. If you look carefully on this one, for n equal to 3, on this sum we would get 6 terms. Here we have only 4. It's a different one. So here you can see in the first and the last one we have x1, x2, and then minus x2, x1, and x3 added. And then here we have x1, x2, and x2, x1, and x3 to the left instead. So following this same pattern, we can also construct this for the general case of an n-ary totally associative algebra, and it gives an n Leibniz algebra with some extra properties. Similar to Lie triple system, we have some parts which are skew symmetric and the remainder which is not. So to here is what I have for you now. Thank you very much for coming, and if you have any questions, please ask. Thank you.